It is a great pleasure to provide the introductory comments for this Nobel Conference lecture by Professor Sir Harold W. Kroto, Royal Society Research Professor at the University of Sussex in England. He and two other scientists, Robert Curl and Richard Smalley, were awarded the 1996 Nobel Prize in Chemistry for their discoveries of fullerenes, which, to quote from the Nobel Foundation, are a family of clusters of carbon atoms bound in the form of a ball. The most familiar of the fullerenes is Buckminster fullerene, a molecule of 60 carbon atoms shaped like a soccer ball. It is named after Buckminster Fuller, the architect of the geodesic dome. This molecule has become known as the buckyball. I began a brief look at Professor Kroto's accomplishments with a quote. The spirit of this anti-hero pervades the whole movie, although he is seldom seen. Indeed, he makes his first appearance late on the movie in the black shadows of a dark street in Vienna, when his face is suddenly illuminated by a light being switched on. That quote is from Professor Kroto and describes the character played by Orson Welles in the movie The Third Man. Professor Kroto points out that the buckyball in some ways resembles that character. Like the Welles character, Buckminster fullerene, the beautiful soccer ball-shaped carbon molecule, had long been lurking in the shadows of soot, such as that from a candle flame or a campfire. As was the case with the Welles character, an extraordinary amount of work, creative insight, interdisciplinary training and collaboration, and intellectual risk-taking were required to flush the buckyball out of its dark abode. The result of this effort was the characterization of heretofore totally unknown forms of carbon that, since their initial preparation, have led to entirely new areas of chemistry, physics, and materials science. As an example, a recent exciting result is the preparation of chloroform fullerene materials that exhibit extraordinary high-temperature superconductivity. There is hope from this research that this line of research might eventually lead to materials that have room temperature superconductivity. Before his work with fullerenes, Professor Kroto was a renowned molecular spectroscopist and had characterized many molecular species that had been thought to be extremely difficult or in some cases impossible to make. These include, among many others, the first examples of compounds containing carbon to phosphorus double bonds. He and his co-workers also investigated cyanopolyalkynes, a family of long-chain carbon molecules capped at one end with a nitrogen atom. These unprecedented, structurally startling molecules were discovered in interstellar space through radioastronomy, in addition to being synthesized in the laboratory. Professor Kroto has a broad range of interests in physical science. He has a similarly broad range of interests outside of scientific research. These include graphic design, art, communication of science to non-scientists, especially to young people, and the support of human rights efforts, such as the work of Amnesty International. Professor Kroto's work with spectroscopy of unusual molecules and with fullerenes has led to many awards and honors. Among them are the Tilden Lecturer of the Royal Society of Chemistry, election as a Fellow of the Royal Society of Chemistry, the International Prize for New Materials from the American Physical Society, the Hewlett-Packard Europhysics Prize, the Nobel Prize in Chemistry, and a knighthood which was awarded in 1996. I now turn the lectern over to Professor Harold Kroto.
Okay, she's not up there. Okay. It will be. Get this microphone. Okay, can you hear me? Is there a reverberation? Okay, well, it's a pleasure to be here, to come back to Gustavus at this auspicious time, and it's quite a daunting event. and obviously we have to look into the future. That's what it says. I've always had great difficulty at this. In fact, I've not even understood what was going on today. Never mind tomorrow. However, I would like to give you an idea of what I think science is about, first of all. And an image I think I showed the last time was of Jacob Bronowski playing with his grandson. And I don't know how many of you gave this toy to your children. Can you put your hands up if you did? How many did not give it to their children? Okay. Well, there was one child who shall be nameless, who every time he picked up the cube, he tried to put it through the round hole. Every time he picked up the pyramidal structure, he tried to put that through the round hole. Every time he picked up the sphere, he tried to put that through the round hole and got it right that time. His mother decided to take him to see a psychiatrist because she realized that if this went on, he might not get to Gustavus Adolphus College. And the psychiatrist analyzed this and said, "Don't worry. This child, it doesn't matter what the problem is, only sees one solution. There's a perfect career for such a child, and that's to be a politician." Mrs. Blair. Okay. Now, of course, it does depend which country I am in, which politician I choose. However, let me say that shapes and patterns are absolutely essential to our understanding of nature. In fact, I believe they are important and fundamental to our understanding of anything. These structures were discovered in Scotland. They're 4,000 years old. They were found at the site of the first Glasgow Rangers versus Celtic football match. In those days, the spectators were really cultured. They carved the rocks into beautiful shapes before they threw them at the opposition. These structures have the symmetries of the Platonic solids, and that's rather perceptive. It shows that deep in the human sort of appreciation of nature and the world is an understanding of shapes and patterns. In Plato, we find, which is the first chemistry book, in the first place, it is clear to everyone that fire, earth, water, and air are bodies, and all bodies are solids, and all solids are bounded by surfaces, and all rectilinear surfaces are composed of triangles. On the basis of that, the Greeks had 4 elements in their periodic table. A 5th one was discovered, the dodecahedron, shown here, by Hippasus in 540 BC. I don't know which university he was at the time, but he ran around bragging and boasting so much that his colleagues drowned him. Sean O'Brien, one of my co-workers on the discovery of C60, said, "There's a lesson here for everyone." However, those patterns are really quite interesting, and they're the basis of everything. And I'm now going to teach you chemistry in 30 seconds. Newton invented classical mechanics to explain how the planets orbit the sun. But it could just as well be an electron orbiting the nucleus. And so quantum mechanics, which I think is the greatest intellectual advance of the 20th century, was invented to explain how electrons orbit the atomic nucleus. And if we look at the work of Van Vleck, a fantastic American scientist, we see in his paper on the anomalous sign of I in Klein's matrices that he said practically everyone knows that the components of total angular momentum of a molecule relative to x, y, z fixed in space satisfy commutation relationships of this form here. Now, when I arrived at Minneapolis Airport yesterday, I asked half a dozen people whether they knew this. No one could tell me this. But this great scientist said practically everyone knows. What he really means, everyone should know. And on the basis of this equation, we understand the electron in the atom. We understand the bonding of molecules. We understand how you are put together. In fact, we know that angular momentum is quantized and that J has the values 0, 1, 2, 3, 4. And on the basis of those numbers, which everybody knows, we'll put them vertically. And then we think of orientations of angular momentum. It's a vector. I won't go into too much detail. When J is 1, it has three orientations. One up, sideways, and down. Now, in classical mechanics, all the orientations are possible. But for J equals 1, there are just three in quantum mechanics. And when J is 0, there's 1. And when J is 5, when J is 2, there are 5 orientations. So the simple numbers 0, 1, 2 map on the numbers 1, 3, and 5. Now, not everybody likes numbers. Not everybody likes mathematics. So I'll simplify it by putting a box there. I'll put 3 boxes and 5 boxes, and let's throw away the numbers. There are 2 electrons to each box, so let's double up the boxes. Okay? Push them together. Move that one there, that set there, this one. I've done nothing but move the boxes around. I'll double up those 2 and put another 2 down below there. And put those 6 below there, and then move them around. And what have we got? The periodic table. Now you all know that the periodic table, which explains the whole of chemistry, the whole of biology, all the chemistry that goes on in your body, the deep understanding of those processes is based on the numbers 0, 1, 2, 3, 4. How much simpler could it get? All of chemistry, all of biology, and all the useful bits of physics. It's there for you. Now, Dirac's equation here, a beautiful equation, explains how light is emitted by the hydrogen atom on the sun, bounces off my face into your eye. This equation is the fundamental equation which governs the interaction of light with matter. 99% probably of your information comes through this equation by the way you see. Now, let me go on. I'd like to say a little bit about the discovery of 660. I talked about it a lot the last time, but it really was work with the radio telescope in Canada which really opened up this particular area of science for me. Because Charlie Townes in the 60s not only invented the laser, or really built the laser and then showed how the laser could be produced, but he turned his attention to space. And he found that in these black clouds in space, these molecules were to be found. Carbon monoxide, water, ammonia, ethyl alcohol, ethanol, enough alcohol to make 10 to the 28 gallons of whiskey. That's enough for the students at Gustavus Adolphus College. Just. We were working at Sussex. My colleague Dave Walton was an expert at stringing carbon chains together. And we made this one and that one. And we detected those in the space between the stars. There's a beautiful place around here where you can find carbon. And then I turned my attention to stars. Stars, carbon stars. And we know that hydrogen is squeezed into helium. 4 hydrogen atoms or 4 protons are squeezed into helium. And 3 helium nuclei are squeezed into carbon. And 4 squeezes into oxygen. Then the star blows up and blows the carbon out into space. Every single carbon atom, every nitrogen atom, every oxygen atom in your body was once inside a star like this. This is Mother. Hello, Mummy. Your carbon atoms were then blown out into space. They traveled around in space for ions or aeons and ended up here in the biosphere in this room today. And you're bloody lucky to be here because most of the carbon atom is still out in space. Most of the people who could be in this room are still out in space. And a large number of people who should still be out in space, I believe. Well, in 1984, I visited Bob Curl at Rice University. And he told me to go and see Rick Smalley because Rick had invented this fantastic apparatus that could produce plasmas from metals. And I went to see it, and I wondered whether the plasma, a laser, vaporizes the metal here, the plasma comes out and goes into a mass spectrometer at this position. I wondered whether this plasma might be rather similar to the plasma around a star if we put carbon here. And that's what we did in 1985. And I want to show you 2 people, in fact 3 people, Jim Heath and Sean O'Brien and Yuan Liu, because these were the students who were involved with us. These were the young students who really did all the work. We could sit, and I could sit in front of the video screen and just look at the data. And of course, many of you know that Rick Smalley, Bob Curl, and I got the Nobel Prize, but the students, well, they got a bloody good meal at McDonald's out of it. You know? No, the real point is it is a team effort. The prize can only go to 3 people. And in a sense, the downside of this prize is that they don't share in it quite in the same way, but they should do, and it's important for our youngsters here to realize that the science is done not just by old geezers like me, but also the young people who work with, and particularly Jim Heath, who is now an outstanding professor at UCLA, Sean O'Brien is at Texas Instruments, and Yuan is at Oak Ridge, all carving out wonderful careers for themselves. But what we discovered was something very interesting. Instead of the carbon chains that I'd suggested we look for, we discovered a big surprise, that there were some clusters, C60 clusters, that had the shape of a soccer ball, and that was a big surprise. At Sussex, we extracted it, and 3 or 4 days later, a Nature paper came and dropped on my desk with these beautiful images of Kretschmer and Huffman and their co-workers. And Kretschmer and Huffman deserve a fantastic credit for what they did because they extracted it. And from that onwards in 1990, some 15,000 papers have been seen. This is the group, Bob Curl in the center, Rick Smalley, Sean O'Brien, and Jim Heath, who were involved in the work at Rice University. And my co-workers, Jonathan Hare, Abdul Sadar, Roger Taylor, and Dave Walton, who first got me interested in carbon chain molecules, and I owe them a tremendous debt. Well, let me go on, because now you can do fullerene chemistry. I'm not going to talk about that. There are some thousands of papers of fullerene chemistry. There's nanotechnology. We at Sussex have been working on that for the last 10 years. I'll show you a little about that later. Recently, we've been able to make a wire which is at nanoscale dimensions, which is sheathed by an insulator of molybdenum sulfide. It's very beautiful. Maybe we'll make computers in the future which will sit in our pocket, supercomputers in our pocket. After all, we've got a supercomputer in our head. We've got beautiful images of iron inside the nanotubes. We can produce non-carbon technology which is really, truly beautiful. It's that aspect that I want to deal with today. When man ate from the tree of knowledge, he elected to find a shortcut to the Godhead. He attempted to rob the Creator of the divine secret, which to him spelled power. What has been the result? Sin, disease, and death. That's pretty laughable coming from Henry Miller, it seems to me. When you think of antimalarials and penicillin and all such things as the Haber process, which since 1919 has managed to feed some 60 to 70% of the world. I think at this time when science and technology are so powerful and dominant, it's so efficient that because it gets it right 9 out of 10 times, when it gets it wrong, all society uses science and technology and gets it wrong. Then we start to complain. 9 out of 10 is pretty good at an exam, right? Yes? I hope you agree with me. If you had got that at university, you'd have been very happy. Well, science, I believe, does that. We see in William Blake, fantastic poet, art is the tree of life, science is the tree of death. I believe he has got it wrong, really wrong, because as we know, many of us, in anesthetics and other areas, science has been really the tree of life, as well as the arts. I could put them both together. But we do have champions. Wordsworth says, the beauty and form of a plant or animal is not made less, but more apparent, as a whole, by more accurate insight into its constituent properties and powers. But there are very few on the art side who actually see this beauty. But let's see a bit of this. This picture, which I think is one of the most beautiful images I've ever seen, It's as beautiful as any flower I've seen, was in Nature about 3 weeks ago. It's a stunning image. And I'll show you some images that I think are equally beautiful. These are some images of C60 molecule from the web. And this is C70. And we can make crystals of C60. And we can make crystals with ferrocene. In fact, a system very similar to this, only 3 weeks ago, was shown to be a high-temperature superconductor. Instead of ferrocene here, they had bromoform. The exciting prospects of producing electricity and transmitting it without loss are on the verge of being achieved. We made large molecules such as this, which is a giant fullerene. We made it for fun, but it turned out to be beautiful science. And in fact, we're looking at nanotubes. This is a cross-section of a nanotube. Here's a metal particle, and here we see a little igloo-type cap of carbon. And if you look at the mechanism, it turns out a carbide, which is carbon atoms and the metal atoms, what happens at the surface is the carbon comes out, it segregates, and as it does so, we manage to get a round cap of carbon. And it's not just the statics which is nice, but the dynamics as well. Hemoglobin, the structure of which was determined by Max Perutz, fantastic guy, who spent 22 years determining the structure of hemoglobin. If we look at this particular component and blow it up, we see that it moves. It's a molecular machine. As this moves, the whole hemoglobin molecule, it moves as well. As oxygen is, you breathe the oxygen into your lungs, it transfers to hemoglobin, and the hemoglobin transports it to the parts of your body where it's uses the oxygen to burn the food, and form ATP. ATP is a fantastic molecule. ATP goes to ADP plus phosphate plus energy in your muscles. As I speak, as I move my arms, as you speak, you use up ATP. Charles Boyer and John Walker showed that ATP synthase, a catalyst, catalyzes ADP plus phosphate plus energy to ATP. And what is it? It's a fantastic molecule. It's a piece of protein with a cavity on the inside and 4 positions into which ADP plus phosphate go. If you look from the side, we have a rotor up the center, we have the outer cavity, and what happens is that a rotor at the bottom turns, okay? This rotor turns this armature inside. This all changes shape, and what happens then is that ADP plus phosphate go in and ATP go out. Inside your body are fantastic microscopic electric motors, real electric motors. Biology created those millions of years ago, long before Faraday. I know that if I'd seen this as a young scientist, young student at school, I'd have said, I want to get involved with these. I think the 21st century is the start of a new era of chemistry where we just don't make molecules which just sit there, but molecules that have function, that do things. This stunning image from Nature 3 weeks ago is a pack motor which zips up and down the DNA. And here it is, I showed you at the start. There's the outer ring, and from the side it looks like this. How can anyone look at these images and not say that science adds to our understanding and the beauty of nature? If there's anybody here who says this, the door's open and they can leave right away. Networks are interesting because C60 was a hexagonal network. And we can have flat planes, and we can delineate these with flat planes or positively curved planes or positive and negative curvature and other sorts of planes as well. Now, we British can get away with anything. Okay. Let me go on because I don't see any difference between art and science. They're the same to me. In fact, my first prizes were in graphic art and design, long before I won any at science. But this is a fantastic drawing by Leonardo da Vinci of a truncated icosahedron. Is it any wonder that the Italians are bloody good at football? Here are our underlined multi-walled nanotubes. These are carbon tubes, which are really exciting. But in fact, we've seen these images before, because somewhere in the museum is a picture by Jackson Pollock. This one will cost you maybe $2 million. You can have this one from 200 after I leave here. And these are silicon oxide nanoscale flowers. These are nanoscale structures that we're learning to make. This is the first useful result we've got in my laboratory, because we used this to make the Christmas cards last year. Okay, well, let's go on, because I'll show you something what I think about my chemistry. Because C60 is a very nice molecule, but it's not my favorite. My favorite is one that I worked on really at the start when I first came to Sussex. And with a bit of luck, well, it seems to have, okay, let me go back there, because it's nitrosoethane. It has an oxygen atom, a nitrogen atom, carbon atoms, and hydrogen atoms. But how does a chemist think about it? And this is an important part of my talk. If you're not a chemist, you have to realize that when we see this grouping, we see this fella. Now, what does it look like? Anybody suggest something? A squirrel? Its tail's not long enough. Anybody else? A dog. It's my dog. Because we made it and we determined the structure. And if you look at it, it's got 2 carbon atoms, it's got 3 hydrogen atoms on the end, and it's got 2 hydrogen atoms at the front. So it's got 4 legs and a tail. If I'd had another group on it, it would be a squirrel, okay? It has a head, and it's got a red nose because it's been drinking all night. And if we look from the back, we see the methyl group. And as it's been drinking all night, it wants to find the washroom. Now, dogs have a hard job finding washrooms, but they can find lampposts. And when they do a bit of internal rotation. Now, as Magritte would say, however, and this is the important part, ce n'est pas une molecule. It is a model of a molecule. All right? And chemists can think in this abstract form, this almost surreal form. And that's one of the limitations of science, and particularly chemistry, for those who have not grown up with it. Well, I want to go on to the most serious aspect of what I have to say. The problems for the future, I believe, are very serious. I'm not as optimistic as I used to be. I was a child of the 60s, and I had the great fortune to grow up in the 60s and to be so optimistic. I think I'm optimistic a bit, just. The problems are attitudes, or some of the problems, attitude of science of some very influential people, such as politicians and in the media, the attitude to science of students, and the attitude of the media. Now, I set up the Vega Science Trust some years ago with a BBC producer, and we make programs for television and the internet. We've now made 50 programs, and I'll tell you about those in a short while. But before that, I want to show you something which was sent to me over the internet, because they thought I would be interested in this. Now,
okay, welcome back. We're ready to resume our discussion of the 105th Congress during your visit here for inauguration. And we're very pleased to have with us the Senate Majority Leader, Trent Lott of Mississippi, if you'd help us welcome.
Thank you for inviting me. Good morning. I would like to know, what advice would you give to a prospective student who is interested in following a career path similar to a senator?
Similar to a senator?
Yes.
Well, first of all, I want to encourage you to take maximum advantage of your educational opportunities. We live in a great country. We have a great educational system that's not perfect. We spend an awful lot of money that doesn't always give us the results that we want. But I can assure you, whatever you want, education will help you get a faster start. For instance, when I was in high school, if you were in the so-called pre-college curriculum, you had to take 4 years of science and 4 years of math. A waste of my time, a waste of the teacher's time, and a waste of space. You know, I took physics. For what? Uh-oh, every physics teacher in America is out to lynch me. Physics is great. And I think we need the best possible physics teachers and the best students in physics we can get if you're going into physics or mathematics or science or medicine. But if you want to be a lawyer, and you know that's where you're headed, maybe you'd be better off taking an economics course, a typing course, a computer course, or music, for heaven's sake, because it's good for the soul.
Now, I don't know about you, but the most disturbing aspect of that was the reaction of the students. I was at a conference in Ottawa last year, and it was an attempt to bring the arts and the sciences together. There was Cardinal, a fantastic architect who built and designed the museum in Ottawa of Canadian anthropology. He, I think, is the architect for one of the museums in Washington, but I think his name will be taken off that building. It will be his building, but his name will be taken off it. There was Pinchas Zuckerman, who gave a workshop on the violin, and I was one of the scientists who was to represent science. And after a while, a young woman got up and said, "Aren't you missing the point? As science explains more and more of the universe, doesn't it take away the mystery?" And there was applause, quite a lot of applause. And that, when the applause subsided, I asked, "Why did you applaud? Is it that ignorance of the way the universe works is something to be applauded?" No one answered. But there is a deep need for mystery, for ignorance, because somehow I think many people, are scared of truth and knowledge. And that worries me, especially in the last few weeks. Now, I show you that but come back to it. One of the problems is science and the media. For instance, there isn't a single child who doesn't look at this and think it's a scientist. After all, I've got more hair than that. I can look as mad as this. I can put my glasses on. I wear a white coat, and I've got pens in here. And this was in the newspaper, the Brighton Evening Argus, when our C60 work came out. Carbon copy of The Secret of Life. And a student, well, I put it up on the notice board, and the student said, "Fantastic likeness, Harry." I made him do an extra year for his PhD for writing that. However, can scientists shake off their mad media image? Who is responsible for this image, which comes from Back to the Future? We see the long hair, the somewhat mad expression. The culprit is here. Now, some of you may think that this is the person who discovered those wonderful theories of relativity, of the photoelectric effect, wonderful contributions to science. And you would be wrong. I have a secret for you. No one has known this until today. The person who discovered those beautiful theories is this guy. All right? In fact, at the Smithsonian on Monday, maybe it was yesterday, I can't remember what day it is, but there's a letter which indicates that Albert Einstein was working and thinking about the theory of relativity when he was 16. And it's important for our youngsters to realize that this is the scientist who did it, and not this fellow. The old guys like me are way past it in general. Our youngsters need the right icons. And anyway, he looks a darn sight better than this guy, as far as I'm concerned. And this guy is a Scientologist. Okay, these are the scientists: Jim Heath, Sean O'Brien, and Yuan Liu. And Jonathan Hare, who extracted C60 at Sussex before we got the paper by Kretschmer and Huffman. Another paper from 1977 when we discovered carbon in space. The chemicals were discovered thanks to Canadian work in radio astrology. So that's science and the media. What is the problem? The problem is language. At a Faraday's discussion in 1954 on the study of fast reactions, the German scientist Manfred Eigen asked the Oxford Don, Ronnie Bell, how the English language would describe reactions which were faster than fast. Ronnie Bell replied, "Damn fast reactions, Manfred. And if they get faster than that, the English language will not fail you. You can call them damn fast reactions indeed." Now, that's English for you. In English, we have a saying, hear no evil, see no evil, speak no evil. In Chinese, this is the same saying. In Japanese, it's interesting. Mizaru, kikasaru, iwasaru has a double meaning. Saru means no and monkey. And so, the relationship between monkeys and that are to be understood. Those of you who've been to Japan in Nikko, this beautiful, stunning little statue out of wood, really, sculpture, tells us that in language you have culture which cannot be translated. And the same is true of science. And this is the most important result that I've ever seen, as far as I'm concerned. It is the ultimate proficiency in English of non-English speaking immigrants to the USA related to age of arrival. After the age of 3 to 7, it drops off. So if you're going to teach language after the age of 3 to 7, you're on an uphill slope. I'm suggesting to you that the same curve applies to almost everything that we do. That after the age of 3 to 7, it might be very difficult or more difficult to teach mathematics, analytical behavior, logical thought, music, appreciation of language, obviously. If that's true, then we understand, and should understand, why many of our kids have such great difficulty learning and achieving their real potential. And here's an important aspect. Senior nurses in Britain, they discuss the inability of nurses to do simple maths. They put the decimal point in the wrong place, so patients might receive 10 times more or 10 times less medication than intended. If you think mathematics isn't important, don't go to hospital, folks. My colleague, John Maynard Smith, wrote a paper in which he had this equation. How many of you are familiar with this equation? Put your hands up. Not so many. Well, he put it in, and the editors turned the paper down, and he rang up to find out why. And he said, well, it's a bit mathematical. Do you really need this equation? John said, I really need this equation. I really do. He said, well, why don't you simplify it by cross-multiplying the D's? Now, some of you may not get that. And that's the culture gap from science. There's another one. There were two mathematicians sitting in a restaurant discussing the fact that so few people understood calculus, one of the great intellectual achievements of all time. The other one said, no, it's not as bad as that. It's not as bad as that. The other said, yes, it is. I'm going to go to the washroom. I'll put a bet on it. When I come back, we'll ask the first person we see the simplest possible problem in calculus. So he went to the washroom, and the guy called the waitress over. So she came over, and yes, he said, well, look, when I come back, when my friend comes back from the washroom, he'll come immediately over to the table, and he'll ask you a question. You won't understand it. You don't need to understand it, because I'm going to tell you the answer. The answer is 1/3 x cubed. So she said, what? 1/3 x cubed. 1/3 x cubed. She said, are you sure? Yes, 1/3 x cubed. Okay. So she goes away. The guy comes back to her, drying his hand, and the waitress comes over and he says, oh, we'll ask the waitress, $50 bet, and it's a piece of cake. So he asks the waitress, what's the integral of x squared? And she says, 1/3 x cubed. He looks at her, can't believe it. The other guy thinking, my goodness me, I've won $50 here. And she walks away, and then she goes back to the two of them and looks at them in total disgust and says, plus a constant. Now, there are some social implications in that as well. However, it does tell us that to understand some aspects of science and technology, we have to be met halfway. Many of us do work hard, very hard in public understanding of science. But we do need to be met halfway by everyone, including politicians. Okay, what are we trying to do? The Vegas Science Trust, and that's our website. I hope some of you will visit it. We've really tried very hard to make programs of scientists. My view is that the first revolution in education was the printing press. Because up till then, the only book in the West was the Bible, really, and monks wrote it. They could not write everything. So when the printing press came along, every individual who had something to say could write a book and have it published, and people could read it. The internet is set to bring about a second educational revolution because moving images, very immediate images, which are similar to those that we see on television, are possible. The internet has democratized broadcasting. Everyone can make and broadcast a program, and the media no longer have control. After all, the media basically decide what to show you on the basis of advertising revenue. That cannot be good for education, can it? At last, I think broadcasting is an educational medium. Now, science consists of three components at least. One is the basic store of acquired knowledge. Another is how that knowledge is applied, the technology. And the third, and by far the most important for the creative aspect and for the way that science advances, is the methods of science, how new knowledge is discovered. Vega's aim is to develop platforms for scientists themselves to communicate on the internet and TV. And we've made 50 programs, and some 38 have been shown on BBC Two in the UK. And we hope that similar initiatives will occur over here. We've made programs such as this one on GM foods, and we pioneered a new concept in scientific discussion. We actually had some scientists discussing this, some people who knew something about it. This is a new concept in broadcasting, because when Channel 4 made a program on GM foods, they had a newscaster who was in the chair, who knew nothing about the science and of genetics, or either. They had a protagonist who was very extreme on one hand, and an antagonist who was very extreme on the other hand. So there we had a real problem. There was nobody else, really. There was someone from Greenpeace, the accredited spokesperson from Greenpeace, who started by saying, I don't know any science, I'm not a scientist, and I don't know any genetics. That wasn't good. There was someone from Christian Aid who was neither also, but was representing the third world. There was someone from the industry who was very quiet, but did know quite a lot about it, but was not able to enter into that discussion usefully. And there was a journalist who also didn't know much about science and genetics, but thought it was a good thing. So that's the sort of problem. Well, let me show you a bit of the sort of programs that we're trying to make, and a little small part of that one. It's an hour-long program. That cost me £40,000. Okay? It was not published, or it was not broadcast. It was made for BBC Two, but it led to a series of 10 discussion programs which were shown and were produced together with the Open University. I'll show you a little bit from the second part of our GM food debate to give you a flavor of what we're trying to do.
Try and rehearse as I understand it, what some of the worries are. They are that the genes themselves that are put into plants might become toxic in their host plant, that they might encourage the plant to produce toxic or allergic substances, that they might even reawaken viruses or infectious agents that were dormant before, and that they could potentially spread, and that seems to be a major concern, spread to other plants and have a wide-ranging impact on the environment. Now, Mike, convince me that it couldn't potentially be dangerous.
Well, I think you're asking a very difficult question that can only be answered by extensive trials. And I want to convince you that these trials have been conducted in the case of herbicide-resistant soybeans, for example. These experiments, the original experiments, were done 20 years ago. It's only now, after exhaustive tests on the agricultural performance of these plants, where key features such as stability of the transgene, the heritability of the transgene, and all sorts of toxicity studies that are published and are part of.
Can I just ask, can you hear that? You can. Okay, that's part of one of the programs, but I want to show you some of the other things. One of the outstanding lecturers, in fact, the second best lecturer I've ever seen, the best one, or the best, I have only seen him on film, is Feynman. The second is from Harvard, is Bill Klemperer. He came to England, and I arranged for him to give a lecture at the Royal Institution, and we recorded him. I tried to get Harvard to help me, but they told me to go away. They weren't prepared to actually support or sponsor my recording. But this is the only recording that I know of one of the outstanding American lecturers, Bill Klemperer from Harvard.
You have to believe that I tell you the truth, that carbon monoxide is the second most abundant molecule in the universe. And yet our theory, our equilibrium theory, says there shouldn't be one molecule in the whole universe. It's that extreme. What does this say? Well, it doesn't say that thermodynamics is wrong. Of course it isn't wrong. That's impossible to be wrong. It says that it's totally inapplicable to the chemistry of the interstellar medium, that everything is dynamical, that in a sense it very much resembles the Earth. If you ask what is the equilibrium status of everything is quiescent, everyone's dead. That's it. And very uninteresting. So we would like something much more dynamic than the thermodynamic equilibrium. And I should say, as a testimony, really, every time I mention that to a group of college students, the audience breaks into tremendous applause if thermodynamics is not applicable. And I wonder why. It might well be that it's so poorly taught that they're just delighted that it doesn't work.
I guess you've all taken first-year thermodynamics. Okay. Let me go and show you a couple of other things that we've been trying to do, and that is really to build an archive of some of the great communicators. We've now got 8 hours of Max Perutz, who discovered the structure of hemoglobin. We've got 8 hours with Fred Sanger, who has 2 Nobel Prizes, one for sequencing DNA. If you want to know who that person is, within perhaps another year, we shall have a website where you'll be able to see and hear interviews with people like Fred Sanger, who have made such a massive contribution to society. Well, let me show you really one reason why I really do science. It's to see a sort of sense of wonder and excitement in students' eyes.
Which is started off in there will stay there. And here I've got a magnet. We've got a very good chance of making it see its own image. In other words, the magnet, as it starts to generate small electric currents in that superconductor, will see an image of itself. So if I were to put the magnet down there and spin it, you will see I've actually managed to get that levitated.
There is actually a gap between...
There's a gap. If I lift it up very carefully, you can look right through there and see the people the other side.
What's going on?
And it's sitting there. Well, it sees an image of itself. So it's actually supported on its own magnetic field. That'll carry on spinning, yeah, but you see, that was the Meissner effect. And now what I'm trying to do is to turn it over, and you can still see through it, and it's still spinning. And that's what's known as the reverse Meissner effect. What do you think it is?
Well, it's got to be attractive, but it's quite...
Now, is it attracted or not? That's a good point. That's a very good way of saying it.
It's attractive and repellent.
Yeah. I'll give you a very quick answer. It's flat spinning.
Now, there's a reverberation. Can you hear okay? Because okay, let me go back and show you a little bit about nanotechnology that we've been doing at Sussex and thinking about. No sound at all. And if you do that, you have a very interesting structure. A tube of graphite with what's called a nanotube, and some people call it a bucky tube. This material is about 100 times stronger than steel. It's 1/6 the weight, and it can conduct like a metal. If we could make this in ton quantities, this material could revolutionize material science in the 21st century. Imagine it. You could make bridges that wouldn't fall down in earthquakes. You could make airplanes which were 10 times, 50 times lighter. That's what this material promises in the 21st century. And it's not imagination. This material exists, but we can only make it in microgram quantities.
Why is that? What's the problems at this stage with...
Yeah, well, it makes itself, and we find these nanotubes in the carbon arc. When we take those 2 carbon rods, and we find that these nanotubes are in there, but we don't know how to control the assembly at this stage. I'm told you can hear it better than I can. Well, that's probably quite good. I'm sick and tired of my own voice sometimes. Let me go a little bit further on and, and say that we need to get out of that. The GM food debate was seen by Lord Jenkin, chairman of the House of Lords Select Committee on Science and Technology, and he said, "I watched with complete fascination. It was by far the best discussion of the issues that I have seen or heard." And the set of debates that were led on from that by the Financial Times said, "The most enthralling program I saw on television last week, in fact, I've seen nothing so fascinating for months, was called The Next Big Thing, Nanotechnology." So there are people who appreciate seeing scientists talking. We're now making programs of science discussions, which we've just seen one of them, scientific lectures, such as that by Bill Klemper of Harvard. I'm most excited by a Young Scientist Day, some programs that we're making now called Snapshots, to give kids at school an idea of what their career might be like. For instance, if they are a design engineer with a Formula One racing team, and something wrong with the car on the Saturday, the suspension isn't working. They work overnight and they fix it, and the car wins. And when they open up the cockpit, Michael Schumacher is asleep, but he still wins. Because he's not the only hero. There are heroes behind the car itself, and they very rarely get seen. And finally, then we have making science archives, and others have too, and finally science workshops for young children. The Vega team is Chris, who's got my computer to work, Jill Watson, who's the manager of the trust, and Jonathan Hare, who you've seen earlier, who is involved with our children's workshops. Now, I don't know about you, but I'd like to do, in the last few minutes, a little poll to find out how many of you had Erectoset or Meccano like this. Can you put your hands up? Quite a lot. How many didn't? Okay, most of those who didn't are under the age of 40, I think. Now, in England, Erectoset, or in fact, the origin of Erectoset is Meccano. In 1901, Frank Hornby invented Meccano, and over 90% of UK scientists and engineers over the age of 40 had Meccano. In the USA in 1913, the Erectoset appeared. I think Gilbert produced it, but it's almost certainly derivative from Meccano. And what we find is an interesting advertising of those days. Meccano boys and girls are keen, ambitious, and inventive. No boy or girl who follows the Meccano hobby can be a bad boy. It keeps him keen, alert, and intensely interested. Teaches him to invent, quickens his thinking capacities, and teaches him considerable manual dexterity. This is very interesting, because it turns out that a huge amount of the part of the brain is involved in manual dexterity and manipulation. And I'm worried, because Meccano is no longer there. In a sense, Lego has taken its place. And Lego is a snap-on brick, which does not teach you nuts and bolts, triangulation, and engineering skills. What should happen is, how many had Lego? Actually, less than I thought. How many gave Lego to your children? Yeah, a lot more. But what should happen is the kids should have Lego and then very soon have Meccano, which gives them an idea of nuts and bolts, how to do this, not to misthread them. In fact, if you've ever had a party and you go to the washroom and you can't undo the tap, you know that the last guy didn't have Meccano. Or you're on the road and you break down, you try to get the wheel off, and you know the guy rammed it off with a hydraulic thing, and he never realized that you were going to have to get it off with your arms. A sensitivity to materials and technology is what Meccano gives you. Lego is fantastically good. It's good for initiating interest, but the next step should be engineering materials. And this is what kids can make. That's things that really work in the same way, really, as cars are built. From the underneath it, here is the steering mechanism and also the drive mechanism. The demise of UK engineering, as well as the drop in the take-up of science, is paralleled by the disappearance of Meccano. And you can't make that with Lego. Anyway, let me finish off. We run workshops for young children. This is a workshop in Santa Barbara with Hispanic kids. I tell them the story of the buckyball. I tell them that, Einstein was not the guy, it was the young Einstein that did it. And I talk about Jim Heath and Sean O'Brien and Yuan, who worked with us, as did John Hare, on the great discovery of C60. And that is a soccer ball. And there are the pentagons on soccer balls, and those are very important. And we make models. Here's a kid in England making the models. Here back at Santa Barbara. I just love this guy who's making this model here. We know this guy is going to solve some of the future problems. We get them to sit around and work together making models here in the UK, again back at Santa Barbara, and they're proud of what they do when they've made it. In Japan as well. I'm going to be in Japan in a month's time, and we're intending to internet broadcast to some 2,000 Japanese kids these sorts of workshops. The internet is going to make that possible. This is a fantastic guy. This is the first person to find a use for C60. We teach them algebra. For instance, take a cube. And children of the age of 6, 7, or 8 have no difficulty with algebra. Because how many faces? 6. They've got no difficulty in counting the number of faces. How many corners? No difficulty in counting the number of corners, 4 on the top and 4 on the bottom. And no difficulty in counting the number of edges. What about a tortoise? Oh, let me go on. And then adding 6 plus 8 is 14, minus 12 is equal to 2, which is Euler's law for any polyhedron. Talked about nature, where we find that there are hexagons and pentagons. And without the pentagons, the shell would be flat and not curved, and it'd be bloody drafty up the backside, especially here in the winter. Insects, the eye of this Australian fly has the same topological structure with hexagons and pentagons, and the pentagons are needed for closure. We talk about the structure of these things, that the size of C60 to a soccer ball is the same ratio as the soccer ball to the earth. We talk about big things and small things. A school in Sussex was the first in the world to make C60. And not only that, they linked it to art and sculpture, because this was put into the playground, where they took strips of plastic to make a large model of a buckyball. And only this week, or this was last Wednesday, in San Luis Potosi, in Mexico, we did a workshop with 220 young kids. And it was fantastic. I've never done it. I've always done it with only 36, which is more intimate. But in fact, a basketball stadium was set up. The kids all had T-shirts, and it was really superb. But this is interesting, because they built one and they drew on it. And let me draw your attention to this. Here are the World Trade Center towers that they drew on this buckyball in Mexico. Well, I'll just show you a little bit of this, because it was really one of the most exciting events that I've ever been involved with. To give you an idea that kids can enjoy science, and something that's rather important.
Auditorio, sean tan amables de salirse, por favor, o de apagar su cigarro. Por favor, las personas que están fumando dentro del auditorio se les suplica que apaguen su cigarro o sean tan amables de salirse.
Yo más bien estoy grabando.
I hope you enjoyed that as much as I do. I've got one last thing to say. I have a colleague at Sussex, Sir John Cornforth, Nobel laureate in chemistry. He's one of the greatest men I've ever come across. Truly, I think, one of the very few, if the only genius that I know, personally. I've met some very clever people. And in a wonderful article, which has been very important in my development, he discusses doubt. That doubt is the fundamental quality that everyone should have. That science and technology and what it has achieved, I say 9 out of 10, has been achieved through doubt. In fact, I think the Royal Society's motto either is or was supposed to have been, take no man's word for it. It's a very important thing, and I think at this juncture, at this point, in the last few days and last few weeks, doubt is very important. And the antithesis of doubt is conviction. And I would ask some of you to think about conviction, because my belief is that conviction is the square world which I find myself in. And my talk is science, a round peg in a square world. And I think that's what I would like many of you now to think about, that there are many people who are as convinced as some of you are that they're right. And I believe that if more children were taught doubt, you would not have had the problems that we've had 3 weeks ago. I want you to think, but what I thought was the worst image I saw 3 weeks ago, and it was actually of a 5 or 6 year old child with a green band around his head, dreaming and aspiring to be a suicide bomber. That was the worst image that I saw. I want you here to think about it, because there are people there who are as convinced as many of you are that they're right. And John Cornforth wrote this wonderful article because he walks every day past a statue in mine and his hometown of Lewis. And Lewis is very important to Americans because Thomas Paine lived there for a very long time. Thomas Paine discussed matters in a pub in Lewis, the White Hart, which is actually now a Best Western, rather nicely. And it was there that he developed some of the very important principles that were important to the development of the USA. Every day, Sir John Cornforth, who has been deaf since the age of 20, and he got the Nobel Prize, walks past this and he points out that this monument is to 17 Protestants who were martyred by the Catholics when they returned. And now, some hundreds of years later, we still look at this monument and think it is something that we should respect. Because the people who killed those 17 were just as convinced as the 17 were that they were right. So I'm asking you to think very carefully about doubt, because I believe, as does John and others, that doubt is the reason that we're here today. I think celebrating science and what science has done for humanity. My favorite card, because I collect postcards, is this one. It says, "I am an alien creature. I was sent from another planet with a message of goodwill from my people. The message says, 'Dear Earth people, when you finally at last destroy your planet and have no place to live, you can come and live with us. And we will teach you how to live in peace and harmony. And we will give you a coupon good for 10% off all deep dish pizzas too. Sincerely, Bob.'" I love this one. I always show it because this person, Stein, he's got a beautiful book. Actually, I believe epitomizes what many of us are worried about today, about the world which we're living, and the one that we're bringing up our children in. But he has a sense of humor. And I don't think we are going to survive without these two things. One is a sincere understanding of our problems, a real understanding of doubt and whether our convictions, which we've been brought up and we instill often in our children, are correct. Because after all, the majority of the world have different convictions. And I ask you to think about that, because I believe that the only great display of magnanimity and humanity in this century was the American approach after 1945 and the Marshall Plan. I think that the US showed true statesmanship at that time in a way that I think we should all admire. And I think it made a tremendous impact. And we see a Europe with European countries together at this time in a way that would not have occurred had the same attitudes been in place in 1945 that were in place in 1918. Finally, I show you my favorite image. It is that science can make kids look as happy as that. Thank you very much.